Good morning. Today we will discuss sets synopsis. Already we completed theory. Now we will discuss once total synopsis of sets topic. Now, first, what is set? It is set. Set is a collection of well-defined objects. Collection of well-defined objects. We know the collection of objects now. But what is well-defined? Well-defined means we can definitely decide whether a particular object or element belongs to the collection or not. Means we can definitely decide any object belongs to or not belongs to that collection. I will explain by taking an example. Example. Collection of all boys in our class. Collection of all boys in our class. It is a well-defined collection because we can definitely decide if a boy is selected, belongs to the collection or not. We can definitely decide. That's why it is a well-defined collection. I will write one more example. Collection of three intelligent boys in our class. It is not a well-defined collection. Collection of three intelligent boys in our class is not a well-defined collection because three intelligent boys. According to me, some three are intelligent. According to some other three are intelligent boys. So it is not well-defined collection. It is simply a collection. So it is not set. It is a set. Okay. Generally, sets are denoted by capital letters. For example, like this. A is set. So I'll write like this. 1, 2, 3, 4, 5. This is set. So I'm taking one more. X is such that X is a prime number. These are the examples of sets. In generally, sets are denoted by capital letters. Capital A, set of 1, 2, 3, 4, 5. Here, capital B is a set. X is such that X is a prime number. Clear? Now, representation of sets. Representation of sets. Sets can be represented in two ways. Sets can be represented in two ways. First one, roster form. First one is roster form. Second one, set builder form. Sets can be represented in two ways. First one, roster form. Second one, set builder form. What is roster form? In this method, we will write all the elements in the flower brackets by separating with comma. In roster form, we will write all the elements within the flower brackets by separating with comma. For example, I'm taking like this. A is equal to 1, 2, 3, 4, 5, 6. It is a roster form because we have written elements of set within the braces by separating with comma. So this is roster form. Next, set builder form. In this method, we will write common property. In this method, we will write common property which satisfies all the conditions. In set builder form, we will write common property which satisfies all the elements of given collection. So here, I will write the same set in set builder form. X such that X is a natural number. X is less than 7. Here, X such that before such that is there, that is called element. After such that is there, that is condition. The element is X. The condition is X is a natural. That X is less than 7. Okay. See here. Observe now, both are same now. This is roster form. This is set builder form because A is equal to X. Here X is the element. What is that X now? X is a natural number. What are the natural numbers? 1, 2, 3, 4, 5, 6, 7. All are the natural numbers. But one more condition is there. That natural number is must to be less than 7. What are the natural numbers less than 7? In generally 1, 2, 3, 4, 5, 6. Okay, this is roster form, this is set builder form. Next one, empty set. Empty set. Empty set means a set which does not have any element. A set which does not contains any element. So in generally, empty set is denoted by symbol 5 or both are same. This is the symbol of representing empty set 5 or empty set. Okay, both are same. So I will write one example now. A is equal to x such that x is even prime. X is even prime. X is greater than 2. It is a empty set. Why it is empty set? X, what here x is the element. What is that element? Even prime. What are the even primes? 2. Only one element is there, that is 2. But one more condition is there now, that even prime must be more than 2. So there is no even prime which is more than 2. So here there is no element. There is no element which satisfies this condition. That's why it is a empty set. Okay. Now, finite set. What is finite set? A set which is empty or contains definite number of elements. Check it again now. A set which is empty or it contains definite number of elements, means countable elements. Then that set is called finite set. Otherwise, it is infinite set. See, I will write now. A is equal to x such that x is a natural number. X less than 0. I am writing like this. X such that x is a natural number. X is less than 0. So what is the element of x? What is that x? It is a natural number. In generally, natural numbers are 1, 2, 3, 4, 5, 6. These are the natural numbers. One more condition is there. That natural number must be less than 0. There is no natural number which is less than 0. That's why it is a empty set. Okay, empty set means it is also finite set. Okay, now I will write one more example. Set B is equal to x such that x is a natural number. X is less than 4. I have written like this. Okay, here what is the element? X is the element. What is that x? It is a natural number. It is also less than 4. What are the natural numbers which are less than 4? Generally 1, 2, 3. Okay. It contains definite number of elements. Definite number of elements is nothing but it is countable elements. What are the countable elements from here? Only 3 elements are there. It is countable. That's why this set is also finite. So already we discussed in the definition. What is the finite set definition? A set which is empty or contains definite number of elements. Here this is empty set. It is also finite. It contains definite number of elements, means countable elements. That's why it is also finite set. A set which is not finite, that is infinite set. I will write one more example. Example from C is equal to x such that x is a prime number. X is a prime number. It is infinite set. Why it is infinite set? I will write like this. What are the prime numbers now? 2, 3, 5, 7, 11, 13. Is there any end for prime number now? No. It is continuous. Okay. So there is no end point. There is no end point means there is no end element also. Okay. So all these are prime numbers which are not countable. So we cannot count them. So up to infinity there are so many prime numbers are there. So that's why it is a infinite set. Okay. It is infinite set. I will write one more example. N is equal to set of natural numbers. What are set of natural numbers? 1, 2, 3, 4, 5, so on. All these are natural numbers. Can we count? No. Natural numbers are uncountable numbers. So these are Okay, this one is infinite. Okay. Finite set, a set which is empty, contains definite number of elements. Next. Equal sets. What are equal sets? Two sets are said to be equal if they have exactly same elements. Two sets are said to be equal sets if they have exactly same elements. See here, I will write like this. A equal to 1, 2, 3. B equal to 1, 2, 2, 3, 3, 3, 3. Are they equal sets now? Yes, these are equal sets. Why? What are the elements in set A? 1, 2, 3. What are the elements in set B? Here also 1, 2, 3. So repetition of the elements in set is not allowed. It means only one time only. So it is nothing but again 1, 2, 3 only. So if 10 times also there, we will count as one time only. Repetition of the elements in set are not allowed. Means it is both are same only. So A has 1, 2, 3 elements. B also have same elements 1, 2, 3. That's why we can say A equal to B. Okay, these two are equal sets. Next, equivalent sets. So equal sets is different from equivalent sets. So equivalent set. The two sets are said to be equivalent if they have exactly same number of elements. They have exactly same number of elements, not same only, same number of elements. So I will write A equal to 1, 2, 3. B equal to 7, 9, 11. These two are equivalent sets. Why these are equivalent sets? A has 3 elements, B also has 3 elements. So number of elements in A equal to number of elements in B. That's why the two sets are equivalent sets. Equal sets means they should contain exactly same elements. Equivalent means they should contain equal number of elements, not necessary same one. Compulsory they should number of elements in first set, number of elements in second set must to be same. Okay. Next most important concept, subset. Subset. See. Capital A comma capital B are two sets. Capital A comma capital B are any two sets. Capital A is said to be subset of B. Capital A is said to be subset of B if every element of capital A is also element of capital B. Every element of capital A is also element of capital B. See here. For example, I am taking like this. 1, 2, 3. B is equal to, I am taking like this. 1, 2, 3, 4, 5, 6, 7. Here, A and B are two sets. Every element of capital A is also element of capital B. Here, what are the elements in A? 1, 2, 3. So those 3 elements are there in second set also. That's why we can say A is subset of B. A is subset of B. The symbol for subset is like this. A is subset of B. See here. A is equal to, I am writing like this, 1, 2, 3. Okay, this is set. Now I want to write all subsets. Okay, all subsets of A. So what are the subsets? Set 1, it is a subset of A because here 1 is there, here also 1 is there. Every element of this set is element of this set. This one is subset of this. Next, set 2, this is also subset. Set 3, this is also subset. Set 1, 2 is also subset. Set 1, 3 subset. Set 2, 3 subset. Is there any other? Yes. 2 more subsets are there. One is itself. 1, 2, 3. A set is subset of itself. 1, 2, 3 set is there. That 1, 2, 3 is subset of itself. Okay. Now one more subset is there. That is null set. Okay. All these are the subsets of this set. Clear? Just count it now. How many subsets are there for A? 1, 2, 3, 4, 5, 6, 7, 8. So 8 subsets are there. N of A is equal to M. Most important part. N of A equal to M means the number of elements in set A is M. Then number of subsets of capital A is equal to 2 power M. Number of subsets of capital A is 2 power M, where M is number of elements in A. Check it this example. Now, here how many elements are there in A? 3 elements are there. Number of subsets 2 power 3. 2 power M only, na? In place of M, 3 is there. 2 power 3, that is 2 into 2 into 2. 8. Correct? Now, I will write one more example. I'm taking like this one. A, B, C, D. 4 elements are there. What are the number of subsets, ma? 2 power M. That is 2 power M means number of elements. 4 elements are there. So answer 2 power 4, 16. Okay. Now A is equal to, I'm taking X comma Y. Only 2 elements. So how many subsets, ma? 2 power M. 2 power M means 2. That is 4 elements. Correct? No. I'm taking A is equal to some 1 or some X. Okay, number of subsets for this one, ma? 2 power M. 2 power M value, ma? 1. That is 2. Correct? So number of subsets for set X are 2 power M. That is 2 power 1. That is 2 only. Next, I'm taking one more example. A equal to null set. A equal to null set. Number of subsets, ma? 2 power M. M means what? Number of elements in null set? 0. 2 power 0. 1. So, number of subsets for null set is 1. Correct? So, number of subsets for any other set, okay, any set, that is 2 power M. So, simply remember, number of subsets formula 2 power M. Next, proper subset. This is also most important. Proper subset. A set capital A is said to be proper subset of B if A not equal to B. Okay, A not equal to B. A set capital A is said to be proper. Okay, a subset capital A. Will write again here. A subset capital A of set B is said to be proper if A is not equal to B. See here, I will write one example. Some X equal to 1, 2, 3. Okay, 1, 2, 3. Now I will write subsets now. Set 1, set 2, set 3, set 1, 2, set 1, 3, set 2, 3, null set, and set 1, 2, 3. These are the subsets. Total how many are there? 2 power 3. That is 8 subsets are there. In that, this is 1, 2, 3. It is nothing but X again. X again. So except this set 1, 2, 3, that is itself. Except that set, all remaining subsets are called proper subsets. So proper subsets are, all these are proper subsets. This is not proper subset. It is a subset, but not proper. Now we can guess easily, if A has M elements, then number of proper subsets of capital A is, you can guess easily. What are the number of proper subsets of A? 2 power M minus 1. Why it is minus 1? Because we are removing itself. Itself is also subset, except that subset, all remaining subsets are proper subsets. So, number of subsets formula 2 power M. Number of proper subsets formula 2 power M minus 1. You can remember. So this is most important formula. Number of subsets formula 2 power m. Number of proper subsets formula 2 power m minus 1. Next, most important concept now. Power set. Power set. Set of all subsets of a set. Set of all subsets of a set is called power set. Set of all subsets of a set is called power set. In generally, power set of a set is denoted by P of A. P of A means the power set of set A. P of A. Clear? No. I will write one example now. See. A is equal to, I'm taking same example now. A, B, C. I'm taking this example now. Now, I will write subsets. Set A, set B, set C. These are the subsets. Next, set AB, set AC, set BC, set ABC, and null set. These are the subsets. We have to write all the subsets in the form of set. So we have to write all the sets in a set. This set is called power set of A. Power set of here. Power set definition is set of all subsets of a set is power set. Now, just you can guess easily, if n of A is equal to m. Most important concept. This one also. N of A equal to m means number of elements in A is m, then number of elements in its power set. You can guess easily. What are the elements in power set now? Subsets. How many subsets are there? 2 power m only? That is 2 power m. So n of A equal to m, then n of P of A equal to 2 power m. Next, universal set. What is universal set? A set which contains all the elements of the given set. A set which contains all the elements of given set is called universal set. Generally, universal set is denoted by capital U. Check it, ma. I will take numbers. A 1, 2, B 7, 8, 9, C 2, 4, 6. These are the given sets. So, what is the universal set? The universal set is a set which should contain all the elements of given set. Given sets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe extra also. Compulsory the set which contains all the elements of given set. Indirectly, it is a superset of all sets. Okay, superset of all sets. So this set contains all the elements of given sets. That's why it is a universal set. Okay. Now, subsets as intervals. Subsets as intervals. We have 4 intervals now. 4 intervals. One is open interval. One is open interval. Second one is closed interval. Closed interval. Next, left open interval. Left open interval. Next, right open interval. Left open interval, right open interval. We'll discuss one by one. Open interval. The symbol of open interval. It is like this is the symbol of open interval. So, what is the open interval meaning? So, its value is x such that x is a real number. That real number must be lies between a and b. You know, this is the definition of open interval. Here, a comma b, open interval, a comma b. Its meaning is x. It is a element. That element is a real number. That real number must be lies between a and b. So graphically, we will write like this. On number line, we can represent interval. This is total real line. No? Now, I'm taking here a, here b. These are the elements. A and B are the elements on real numbers. So open interval means the elements which are in between A and B. This what is called A and B, open interval, A comma B. Here the open denotes it is not included. Okay. Here A comma B, open interval. So here A and B are not included. The values which are in between X only, in between A and B only, not AB, not included. Okay. Next, closed interval. In generally, closed interval is denoted by like AB. Closed interval AB. Its meaning is same. It is a number X. That element is a real number. X is a real number. That X is lies between A and B, including A and B. Less than or equal. Equal means it is there in the A is also there in the interval. Here less than or equal to B. B is also there in the interval. Okay. This is the definition of closed interval. So we can represent on number line also. Minus infinity. This is plus infinity. A B. Here in between the values means this part. Including we represent with closed. In generally, on number line, we can write closed interval as like this. Next, left open interval. In generally, left open is nothing but right closed. So we can write like this now. A, B, left open, right closed. Here also, X, it is a element X. That X is a real number. That X is a real number. That real number is lies between A and B. Including B, not including A. Left open means A is not included. Right closed, B is included. So on number line, we can write like this. Minus infinity plus infinity, A, B. These are the in between values. Here left open means keep open. Right closed. Closed means we have to close like this. This is the representation of a left open, right closed interval on number line. Next, I lost. Right open interval. Right open interval is nothing but in generally is left closed. Closed A comma open B. So here also it is a real number X such that X is a real number. It is an element. That element is a real number. That real number is lies between A and B. That real number is lies between A and B. Here, A is included because left closed. That left closed means A is including in that interval. Right open means B is not included. Okay? Now we can represent this interval on number line minus infinity plus infinity. It is a total real line. Now these are the elements A and B. So here interval which is lies between A and B. Here left closed, right open. Left closed, right open. Left closed means is included. Right open means it is not included. Okay. These are the intervals as subset of real numbers. These are also subsets. For what? Subsets of real number set. Okay. Next concept now. Venn diagrams. Venn diagrams. These are very simple. No? Venn diagrams are the diagrams which are used to represent the relation between the sets. Okay. Venn diagrams are the diagrams which are used to relate, which is used to relate the sets. See here. In generally, universal set is denoted by rectangle. Universal set is generally represented with rectangle, and all other subsets are represented with circle or oval. Circle or oval. Clear? No. I will explain that. See, A equal to 1, 2, 3. Universal set equal to, I'm taking that is 1, 2, 3, 4. So these two are the given sets. I want to represent the relationship between these two sets using diagrams. These diagrams are called Venn diagrams. See here, A is subset of B. That's why I have written A inside universal set. So what are the elements in A? 1, 2, 3. What are the elements in U? 1, 2, 3, 4, 5. Here 1, 2, 3 are elements also there in universal set. Next, what are the remaining elements now? 4. Okay. Now I will write one more example. A equal to 1, 2, B equal to 3, 4. Universal set equal to 1, 2, 3, 4, 5, 6, 7. So I want to represent the relation between these three elements using diagrams. See here, this is universal set. What is the element? What are the elements in universal set? 1, 2, 3, 4, 5, 6. So these are the elements. Okay. Elements in universal set. Here A and B are subsets. A and B are subsets of universal set. Means compulsory A and B should be inside universal set. A and B are sets which are subsets of universal set. So that's why I have written inside. One more information is there. A and B are disjoint sets. Disjoint sets are nothing but they don't have any common element. That's why I have written separately. This is A, this is B. Okay. What are the elements in A? 1, 2. What are the elements in B? 3, 4. These are the elements. Next, in universal set, 1, 2, 3, 4, 5, 6, 7. Already 1, 2, 3, 4 also there in universal set. So what are the remaining elements? 5, 6, 7. These are the representation of elements. This is one of the examples. We will write one more example. A equal to 1, 2, 3. B equal to 3, 4, 5, 6. So universal set equal to 1, 2, 3, 4, 5, 6, 7, 8. So I have taken like this now. I want to represent this relationship in using Venn diagram. So I want to represent relationship between these three sets using Venn diagrams. So see here. Try to understand. Generally, universal set is represented with rectangle. Okay? Universal set represented with rectangle. Next, here A and B are the subset. Subset should be inside universal set. But here some common elements are there for A and B. That's why I will write like this. This is A set. This is B set. Intersecting set. Circles. Just think. These are circles. Intersecting circles. So here, what are the common elements? First, A and B. Only element 3 is common. Okay, first I will write the common element. Next, what are the elements in A? 1, 2, 3. 3 is also already there. I will write 1, 2. Okay, next. On B, 3, 4, 5, 6. Already 3 is there. 4, 5, 6. On B. Next, universal set is nothing but 1, 2, 3, 4, 5, 6, 7, 8. Already 1, 2, 3, 4, 5, 6 are there. What are the remaining elements now? 7 and 8. Okay. I will write one more example. A equal to 1, 2. B is equal to 1, 2, 3, 4, 5. Universal set U equal to 1, 2, 3, 4, 5, 6, 7, 8. I'm taking like this. Here. First, in generally, universal set is denoted by capital U, rectangle. Okay. Now, A and B are subsets of universal set. It is clear. Observe, A is totally subset of B. A is totally subset of B means A is inside of B. So, this is B. A is inside of B. So, what are the elements in A? 1, 2. What are the elements in B? 1, 2, already 1, 2 is there. 3, 4, 5. Next, what are the elements in universal set? 1, 2, 3, 4, 5, 6, 7, 8. Already 1 to 5 is there. Next elements are 6, 7, 8. These are called Venn diagrams. So representing the relation between the sets using diagrams. The diagrams are called Venn diagrams. Clear? Next. Operations on sets. On sets. So we have operations plus, minus, into, division. In sets also some operations are there. Those are called union, intersection, difference, complement. Okay, some operations are there. We will discuss one by one. First, union. A comma B are two sets. A comma B are any two sets. The union of these two sets is denoted by A union B. This is the symbol. The representation of union with this symbol. Okay, A union B. We call it as A union B. What is the meaning of A union B? A union B is equal to the element X which is belongs to A or B. This is the definition of union. A comma B are any two sets. Union of these two sets is denoted by A union B, and it is defined as A union B is equal to X such that X belongs to A or X belongs to B. So see here, I will write one example. A equal to 1, 2, B equal to 2, 3, 4. Now I want to write A union B. A union B is nothing but the element which is belongs to A or B. Means we have to write all the elements of capital A also B also. So 1, 2, 3, 4. So simply remember, we have to combine the elements of two sets. Combine the elements of two sets. That is union. So we can represent this union using Venn diagram also. This is A, this is B, this is universal set. A union B is represented by this. The shaded part is called A union B. This shaded part is there. This part is called A union. Clear? Venn diagram, definition, example. Okay. Similarly, intersection. A comma B are any two sets. Intersection of these two sets is denoted by A intersection B, and it is defined as A intersection B is equal to X such that X belongs to A and X belongs to B. Try to understand what difference between A union B and A intersection B. Here, X belongs to A or X belongs to B. Here, X belongs to A and X belongs to B. Means the element should be present in A as well as B. Okay, I will write now. Example. Capital A is equal to, I will write same example now. 1, 2. Capital B is equal to 2, 3, 4. Okay. What is A intersection B? What is the definition of A intersection B? It is a element. That element must be belongs to A and B. So the element should be present in A as well as B. It is nothing but common element. Correct? So what are the common elements in these two sets? Only two. This is A intersection B. Now, how to represent Venn diagram? Venn diagram of A intersection B. So, what is A intersection B? Common. Okay, the element which is present in A as well as B. So, common part. So, what is the common part? This part only. And common part. This part is called A intersection B. See here, difference. Difference. What is difference between two sets? Capital A comma capital B are any two sets. Then the difference of capital B in A is denoted by A minus B. A minus B. This is difference. Symbol for difference. A and B are two sets. The difference of B from set A is denoted by A minus B, and it is defined as X such that X belongs to A but X not belongs to B. Means the element should be present in A but not in B. So the element should be present in A but not in B. So I will write example. The same example I will write x equal to A equal to 1, 2, B is equal to 2, 3, 4. Now I want to write A minus B. What is A minus B? The element should be present in A but not B. So what are the elements in A? 1, 2. So 1 is there here, not there. So 1 is the element which is there in A, it is not there in B. So in A minus B there is 1. Next 2 here is there, here is also there. So it is not yet. So what is A minus B? Set 1 only. Now, so we will represent A minus B using Venn diagram also. We can express A minus B using Venn diagrams also. What is A minus B? The element which is present in A but not in B means this part only. This part is called A minus B. The shaded part is called A minus. Clear? Next, complement of set. Complement of set. Capital A without any set. Capital A without any set. Its complement is denoted by A dash. A without any set. Its complement is denoted by A dash. So its meaning is A dash is equal to X such that X belongs to U, but X does not belongs to A. The element should be present in U means universal set. It is not there in A. So indirectly, it is there in U, it is not there in A. Means it is nothing but U minus A only. So A dash is nothing but U minus A. A dash is nothing but U minus A. So we will write one small example. If A equal to 1, 2, universal set I am taking like this. 1, 2, 3, 4, 5, 6. Now I want to find A dash. What is A dash? U minus A only. So what is U? 1, 2, 3, 4, 5, 6. Minus A means 1. U minus A. What is the difference definition? The element should be present in first set but not in second set. The element should be present in first set but not in second set. Here one here is there, here is there. So in difference one will not get. Here 2 is there, here also 2 is there. So 2 will not get. Here 3 is there, here 3 is not there. So 3 is the element in A dash. Next 3 or 4 is there, here 4 is not there. So 4 is element of A dash. Next 5, here is there, here not there. 5, 6 also. So simply remember, difference is nothing but the element should be present in first set but not in second set. So 3, 4, 5, 6. So what is the Venn diagram? This is universal set. This is A set. So what is A dash? A dash is nothing but universal set minus A. Correct, ma? A dash is nothing but total universal set minus this part. Total minus this part is nothing but this part only. This shaded part is denoted by A dash. Clear? Now, some most important properties are there. We will discuss one by one now. Some properties are there. You can use these properties. First property, idempotent. Idempotent property. So, A union A is A. Idempotent property in union. Similarly, in intersection also, A intersection A is also A. Idempotent property in union, idempotent property in intersection. Okay. Next, commutative. Okay, commutative property. What is commutative property? A union B is equal to B union A. It is commutative property in union, operation union. Same in intersection also. A intersection B equal to B intersection A. Clear? Next, associative. associative property in union. A union B union C is equal to A union B union C. In intersection also, A intersection B intersection C equal to A intersection B intersection C. This is associative property in union, associative property in intersection. Next, distributive property. So these are two types of there here also. We'll discuss that. A union B intersection C equal to A intersection C union B intersection C. This is distributive property of union over intersection. This is distributive property of union over intersection. Similarly, one more is there, so we can write that. A intersection B union C. It can be written as A intersection C. Sorry, A union C intersection B union C. Okay. A union B intersection C. A intersection C union B intersection C. Similarly, here also A intersection B union C. A union C intersection B union C. These are the distributive properties. Here, this distributive property is distributive union over intersection. This is also distributive property intersection over union. Okay. Now, most important laws are there. De Morgan laws. Okay. De Morgan laws. Most important laws are there. A union B whole dash is equal to A dash intersection B dash. Next, A intersection B whole dash is equal to A dash union B dash. Okay. Next, law of double complement. Law of double complement. A dash whole dash is always A. A dash whole dash is equal to. Next. Law of universal set, law of pi. Law of universal set, law of pi. See here, U dash is always null set. Null set dash is always universal set. Universal set dash is null set. Null set dash is universal set. Next, one more concept is there. Disjoint sets. Disjoint sets. Two sets are said to be disjoint sets. Two sets are said to be disjoint sets if A intersection B equal to null set. A comma B are two sets. These two sets are said to be disjoint if A intersection B equal to null set. For example, I will write now. A equal to 1, 2, 3. B equal to 4, 5. Like this one. These are the two sets. Now make A intersection B. What is A intersection B? Intersection is nothing but common element. Is there any common element? No. So it is null set. A intersection B equal to null set. So the two sets are disjoint sets. Next, last concept is there. Some most important concept is there. N of A union B equal to N of A plus N of B minus N of A intersection B. Okay. This is most important formula. N of A union B means number of elements in A union B equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. So it is applicable for three sets also. N of A union B union C equal to so N of A plus N of B plus N of C minus N of A intersection B minus N of B intersection C minus N of C intersection A plus N of A intersection B intersection C. So these two are the application of sets. Okay, using these applications we can do some problems. Thank you. If you have any doubt, you can ask.